Deformation Part 2, Joints and Faults. Two basic kinds of fractures. A joint is a break in the rock, whereas a fault is a break along which some movement has taken place. Now in this rock here, you can see horizontal bedding planes, but the vertical lines are joints. Whereas this fault, you can see not only is there a crack in the rock, but some movement has taken place along that crack. What causes joints and faults? When in doubt, you can always blame plate tectonics. Also the weight of burial. Here we have mud cracks forming from the shrinking of the clay as it dries out. Or another example would be columnar jointing as a lava flow cools. Finally, if this were the granite of Yosemite, as the weight above it erodes away, the granite expanded, and the expansion caused exfoliation layering to occur, and you can see that clearly on the back of Half Dome. Here's an example of joints forming in an unusual way. Underneath Arches National Monument, there was salt rising, a salt dome, and as it rose below a layer of sandstone, it formed cracks, and those cracks were a good place for more weathering to occur. And as a result, those cracks weathered into what's known as fins. And every once in a while, one of those fins would erode more from the bottom, and you would get an arch. Hence the name, Arches National Monument, one of my favorite. So here are the sandstone fins, and here is Delicate Arch, one of the most beautiful arches of arches. I hope you all recognize Devil's Tower, perfectly great example of columnar jointing from the cooling of lava. Now for faults. The kinds of faults are dip-slip faults, which are from vertical movement, and you have normal, reverse, and thrust. You have horizontal movement giving you strike-slip faults, left lateral and right lateral, or you could have oblique faults with both vertical and horizontal. Now you can memorize those names, or you can make sense of them by using the terms that you have learned before. The strike, as you'll remember, is a compass direction along this line, the line that a horizontal plane makes with a tilted plane. Now that plane could be a rock layer, or the plane could be the fault. The dip, on the other hand, is the direction in which material would drip down the side of the plane. So if you have a strike-slip fault, that means the movement has occurred along the strike. In other words, that would be horizontal movement. Whereas a dip-slip fault, the movement went down the dip. And an oblique fault means that you have both strike-slip and dip-slip movement at the same time. Before we go any further, you have to understand the concepts of hanging wall and footwall. This whole idea of hanging wall and footwall, the terminology was created by miners. Here's a little miner here inside a mine. Now it's not a surprise that miners were mining along fault zones. That's where hydrothermal veins are most likely to occur, along cracks in the rock through which the hot water could seep and deposit important minerals. As the miner is standing there at the fault, above his head is hanging a wall that he called the hanging wall, and at his feet is the footwall. To give you a specific example, here are friends of mine at the Keenot mine, which is an abandoned gold mine in the Inyo Mountains, and one of my friends got his hand on the quartz vein here. I wish all that yellow stuff was gold, but if it were, this would not be an abandoned mine. Hanging above her head, we have hanging wall or footwall? Well, of course, I just told you a huge hint. It is the hanging wall. So this is the footwall, this is the hanging wall. Here we have a dip-slip fault. In a normal dip-slip fault, the hanging wall on the left has moved down. That's the definition of a normal fault. Now, I can't prove that the hanging wall went down and the footwall stayed the same place. It's just relative to each other. Every normal fault results from tension. That is, the crust is getting pulled apart. The opposite of a normal fault dip slip is a reverse fault, which results from compression. The hanging wall in a reverse fault, hanging wall has moved upward relative to the footwall. It is the upthrust as opposed to the downdropped. Then you have a reverse fault that is at a very low angle. In fact, most reverse faults do tend to be at a low angle. If that angle is less than 45 degrees, we call that a thrust fault. The Los Angeles area is just lousy with thrust faults, unfortunately. A strike-slip fault, horizontal movement, you have, in this example, the side across from us looks like it moved to the right. But that guy looking at us says, no, 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 you move to the right. It doesn't really matter which side you're standing on. The other side looks like it moved to the right. If, however, it looks like the other side moved to the left, you have what's called a left lateral strike-slip fault. So, right lateral strike-slip fault, left lateral strike-slip fault. The San Andreas, one of the most important strike-slip faults in the world, that is right lateral. What kind of fault do we have? Well, we're looking from the side, not above, so that tells you that you've got dip-slip movement. Is it normal or is it reverse? Well, if there were no obvious layers, we wouldn't know for certain. But this layer down here with one thick and two thin ones seems to be repeated right there. So that makes you realize that this side probably went up. So that is a reverse dip-slip fault. Here's the fault line here. In fact, you can even see that this rock layer here started to bend and then it gave up and it just broke. You have downward movement along this side. That's almost a vertical fault, so it's hard to figure out what it is, but it would be a normal fault. Of course, when we use these lovely little diagrams, the world doesn't look like that. Erosion will tend to attack the upthrust side of the fault, and therefore you'll have these mountains left with the layers on the downdrop side not eroded. You can see that all over California. Very distinct edge of a mountain range. For example, the San Gabriel Mountains. They have a fault at the very edge of them. What kind of fault is this? Well, the hanging wall went up and it's about a 45-degree angle. So that's a thrust fault. But notice that the layers above it deformed by bending instead of breaking. They weren't very brittle. The result is known as a blind thrust fault. Blind because it didn't come to the surface, and thrust because it's a thrust fault. The Northridge earthquake is a result of movement along a blind thrust fault. We're looking now at Red Rock Canyon. There's the fault right there, and this would be the hanging wall. This is the footwall. You have to take a look at something that might have been displaced, and there you go. This layer on the right came down. Since the hanging wall came down, that means that it is a normal fault. That means that Red Rock Canyon is under tension. We're looking down at the San Andreas Fault. The fault line is going right through there. This is a stream valley that was coming along and suddenly it shifted. And it shifted to the right, showing you that the San Andreas Fault is in fact a right lateral strike-slip fault. Two faults here. 1, 2, showing the same kind of movement. Hanging wall, footwall. Hanging wall went down relative to the footwall. That's a normal fault. We're looking down in this picture at the DeRose Vineyard near Hollister, California, and you can see definite movement of the vines from one side to another. So that is the San Andreas Fault with its right lateral strike-slip movement. Faults are not always a negative thing. They do a good job of trapping oil. Since oil can migrate through a permeable layer, it will end up at the fault line getting stuck within the impermeable layer, where it can then be drilled.